Hey, AP Chemisters, this is Mrs. Vanderlei bringing you another blank wall. We are in Chapter 17 and Section 5, and we are introducing to you something called free energy, also called Gibbs free energy. And what we call this is the total picture spontaneity. It's a mathematical equation that will give you a definitive numerical value to say, is this spontaneous or not? Let's kind of recap what we've done so far in Chapter 17. We've talked about how what entropy is and how the universe is going to disorder. That's the second law of thermodynamics. We saw how entropy is related to temperature. And then we kind of tied it in as like, how is that related to enthalpy, the heat? And what Gibbs free energy does, it kind of combines those ideas all together with delta H and T and delta S, okay? And he came up with this equation. His name was Willard Gibbs. He was a professor at Yale University. He pretty much lived his whole life in New Haven, Connecticut. He was a brilliant man, really. Einstein gave him many accolades, actually, on how influential he was in his particular field. Anyway, so what Gibbs free energy, what Willard Gibbs even defined, what is Gibbs free energy? He defined it as available energy. And what does that mean? Well, available energy is the greatest amount of mechanical work which can be obtained from a given quantity of a certain substance in a given initial state without increasing the total volume, which is like idea of work, right? And allowing heat to pass to or from external bodies, except such as the close of the processes are left in their initial conditions. Like, what the heck is that? It is the idea of the available energy for a system, for a thermodynamic system. And so this equation, then when you come up with a value of delta G, will kind of give you how much available energy there is for a system to do work, all right? As being like an engineer, that's an important idea. If I have this thermodynamic equation or this reaction, how much work can I do? Perhaps you can see where this is going, because when we burn octane, what does that burning do? It drives pistons up and down to make the engine work and whatnot. And so that is, perhaps a useful interpretation of what the Gibbs free energy is. All right, well, let's see what we need to do in chemistry, though. So here is our equation. This equation is on your equation sheet that you'll be given every time, so you don't have to memorize it, but I'm sure you will after a while. So it's delta G, so Gibbs free energy is equal to delta H minus T delta S. So what about free energy and spontaneity? Okay, so reactions will proceed in the direction that lowers their free energy. So free energy, it says negative delta G, so we're lowering free energy. And that's a really important idea, because if delta G is a negative value, you're lowering that free energy, that means it's going to be spontaneous. And then at equilibrium, delta G is 0. And we really don't know what equilibrium is yet. That comes in a different chapter. Notice how we skipped over in chapter 17. Well, equilibrium was talked about in 14, 15, and 16. So we don't know that yet. We're going to come back and really zero in on this relationship between equilibrium and delta G. But in general, if I look at this picture here, Gibbs free energy determines the direction of spontaneity. And so if you're decreasing it this way, it's spontaneous. Notice if you're decreasing free energy. Notice that's your y-axis, all right? It's also spontaneous. So when you're at equilibrium, when your forward reaction is equal to your reverse reaction, notice there's a double arrow here. That's when delta G is 0. That's when there is no change in that available energy. Okay, so again, we will talk much more about this in later chapters, but for right now, that's good enough. Okay, so let's go to the next page and see how we actually work with these things. Okay, so let's see how the effect of delta H, delta S, and T is on spontaneity. Now, please know that temperature, because it's in Kelvin, is always going to be a positive number. And that's really an important idea when we talk about the idea when is delta G negative and when it's not. So in case number 1, delta H is negative and delta S is positive. So what does that mean? Delta H is negative. Hey, that's exothermic. And delta S is positive, means it's becoming more disorderly. So here's an example of 2 moles of dinitrogen monoxide making 2 moles of nitrogen gas plus 1 mole of oxygen gas. Notice that the delta H is negative, so it is exothermic, it's releasing energy. And notice you're going from 2 moles to 3 moles. Haven't we said these are the most common cases for spontaneous or for something to be spontaneous? Yes, it is. Let's see how that works, okay? So here I'm going to use this equation where delta G is equal to delta H minus T delta S, and I'm just going to look here. Delta H is negative minus a positive number times a positive number. And what does that do for us? All right, so let's say delta H is already negative, right? Let's say this is my negative value, negative 163.2. It's below 0, isn't it? So I'm going to subtract a positive number. Where does that put me on my number line if I subtract a positive? Doesn't it go this direction? And what kind of number will this always, always, always be? Yeah, delta G will always be negative. So what does that mean? That this is always spontaneous. All right, write that down. I didn't. You can do that. So and you have the case of delta H is negative and delta S is positive, it is always spontaneous. Write that down. So let's look at the case number 2. Let's see what happens here. Scrolling down. All right. So case number 2, delta H is positive and delta S is negative. So what does that mean? We have an endothermic reaction, and things are getting more orderly. Let's say we have 3 moles of oxygen gas becoming 2 moles of ozone. Notice that delta H is a positive, endothermic. It requires energy to do that. Notice that delta S is also negative. Why? Because of 3 moles going to 2 moles. Well, how does this work out in my math? All right. So let's check this out. We have a delta H is positive. So delta H, I'm going to start off over here, is positive. That's a positive 285.4 kilojoules. And I'm going to subtract a negative. Well, what does that do for me? Isn't that like adding a positive? So I'm going this direction. Okay, and what does that mean? Delta G is a positive number. Always. And so what does this mean? If we have an endothermic and delta S is negative, delta G is positive, and it is never spontaneous. Will you write that down? Never spontaneous. Okay. So we have an always and a never when delta H and delta S are opposite signs. So what happens when delta H and delta S are the same sign? That either they're both positive or they're both negative. Well, guess what it's going to depend on? Take a wild stab. If you said temperature, you're right. So let's see how this works, okay? So in case number 2 here, actually, I think it's case number 3, isn't it? Delta H is negative and delta S is negative. What does this mean? That it is exothermic. That means heat's going to be released, but we have liquid going to a gas. All right. That's not right. That is also, that's a positive, isn't it? So I think I need to change this. So make this a gas going to a liquid, and that would make a whole lot more sense. Let's do that right now. And how did I know that? I looked at that and I go, that's not right, because liquid going to a gas, that's endothermic. It required energy, so that's why I had to hesitate there for a minute, knowing something was wrong. So now this makes more sense. Delta H is negative. To go from a gas at a high level down to a liquid, it has to release energy to get down there. And if it's going from a gas to a liquid, that is also negative. Okay, phew. I've restored order in our world here. So what does this mean? Well, I'm doing this, aren't I? So delta H is negative minus a T negative, right? So if I were to actually go through this, let's see here. Delta H is negative. I'll put this right here. Negative what? Negative 6.01. And once again, I'm going to add a negative. All right, so I'm going to go in this direction, okay? So when is this going to work? Okay, when does a gas become a liquid? Well, this area right here, it's spontaneous. Right here, delta G is negative. All right, guess what? From here over on, this area right here, delta G is positive. And so at what value will this remain negative? At high temperature or low temperature? Well, hopefully you figured at low temperature. So write that down, is spontaneous at low temperature. And doesn't that make sense? When do you have condensation? When it's hot or when it's cold? Well, if you've been checking your windshields, during these autumn temperatures, I see some condensation on cold mornings. I don't know about you. All right. So when on a hot summer day do you have condensation on the side of your glass when I have ice in it? When it's cold, when the glass is cold, then the gas will condense on your glass and make it wet again. So at low temperatures, that is spontaneous. And so how low? Well, until I get to a 0 point. Okay. So it's temperature dependent. So what about the last case here? Hopefully I got this one right. Let's go on. Well, sadly, I did not get this one right. This is going from a solid to a liquid, all right? So if you'll change that for me. So what's happening here? Delta H is positive, right? Right here. Positive, so that makes sense because it requires energy to melt an ice cube, doesn't it? And notice that delta S is also positive. I'm going from a solid to a liquid. So notice how both signs are the same. So when I go over here, I'm going to have delta G equals a positive number. So I'm going to start here on my number line in the positive realm, positive 40.7 kilojoules. I'm going to subtract a positive. So I'm going to go this direction. So when is it spontaneous? It's spontaneous right here, isn't it? So when temperatures are what? Well, I'm sorry, this is not spontaneous. This is positive delta G. It's not spontaneous in this area, but it is spontaneous at higher temperatures. So if I have a little temperature, it's still going to be a positive number and it won't work. But if I have a big temperature, a big positive number, I'm going to have a small value here minus a big value here, and it's going to throw it into the negative realm. So does that make sense? So will ice melt at negative 20 degrees Celsius? Of course not. Will it melt at 100? Yes, it will. All right. Not only that, it'll probably start boiling. I don't know. But anyway, so the bigger the temperature, the more it's going to go into this negative area. So if I were to put this whole thing together, let me scroll down here. Let's check this out. If we have, this is a chart that's, by the way, really important. If you're using a highlighter, highlight this. If that number line thing doesn't go for you, then commit this chart to memory. Okay, so if it's exothermic and I'm increasing entropy, I am favoring the enthalpy, I'm favoring entropy, guess what? It's going to be spontaneous at any temperature. It's always spontaneous, and it's going to favor the forward reaction. You're going to make a lot of products here, okay? So what if it is the opposite? How about, I'm going to go down here next. What if it's the opposite? What if it's an endothermic and I'm decreasing it? Will it ever be spontaneous? Never. At any temperature? No. At no temperature will it be spontaneous. And what does it favor? I'm not going to make any products, so guess what? I'm only going to make reactants. So what about when I told you that the signs are the same? Well, guess what? It is temperature dependent. Okay. So if I have an endothermic reaction and I have an increase in entropy, when is it going to work? That's just kind of like the problem we just had, wasn't it? When they're both positive. So if I start out as an endothermic, I need to drive it below 0. So I need to subtract a high value, all right, for that to happen. So it's going to favor the product at high temperatures. And then the other one, if it's exo, and then entropy is going to decrease, it's going to favor low temperatures. I don't want it to go too high, otherwise it's going to go, delta G is going to be above 0, and then it's going to go to non-spontaneous. So it'll favor the products at the low temperature. So like I said, you need to commit this to memory. In other words, if you have the same signs, it is temperature dependent. If you have opposite signs, just remember, if you have exo and an opposite sign endo, or a high entropy, so it will always be spontaneous no matter what. If you have the two not very common things, it'll never work, okay? I'm going to stop the video here. Don't wait to be great. We're going to finish off section 17.5 in the next video. So see you next time. Bye-bye.